Okay. Well, as I told you guys a couple of days ago, I was not going to be here on Thursday, so I wanted to record for you a lesson that you could listen to and do some problems from. So, 6.3 is our next section, and it is titled Vectors. Well, what is a vector? A vector is a measure or quantity, right? Measure quantity that includes both I want to stress this, so both a magnitude or size or size and a direction. Two very common vector quantities that you encounter in math, or maybe in physics in particular, are force and displacement. Now, there are all kinds of vector quantities and vector measures, but these are very, very, very common. When we talk about a force, one example of force would be weight. And if we talk about a person's weight, what we mean by that is the magnitude and the direction of the force of gravity acting on the person. Now, an easy way to communicate this is with what we call a directed line segment. Okay, so this is one way that we draw or communicate vector measures. All right, directed line segment. Directed line segment. Now, it looks a lot like a ray from geometry, but if you remember, a ray went on forever in a particular direction. Okay, so this arrow here, if you will, this guy doesn't keep going on and on. The length of this thing, the length of this directed line segment would communicate the magnitude or the size of the vector. All right, length. All right, we would associate with magnitude. Okay, the amount, if you will. All right, and the arrowhead indicates direction. Okay, so if for you guys that have had physics, you know that that weight is always thought of again as it's the gravitational force acting on a mass, and it's always measured perpendicular to the ground. So, you know, if you had the ground here, then you would show the weight of the person pointing perpendicular to that. Okay, that's how we understand force. All right, so there's a magnitude and a direction to it. Right. Displacement's another common vector quantity. If let's see, if Juliet, while she's in Girl Scouts, is on a hiking trip with the Girl Scout troop, and she wanders away from the campfire. Here's the campfire. That's my cool little fire there. There are my logs on fire. Okay. And so if Juliet wanders away, all right, here's Juliet out here. It's not enough in order to locate her. It's not enough to know how far she is away, right? We have to know not only how far she is away, but in what direction she is. So again, this is just an example of a vector quantity. This is this directed line segment is indicating a position or a displacement. Displacement meaning that she's displaced from the origin. But it doesn't mean that she's just so far away from the origin. It also means in a certain direction. So, you know, you might say something like Juliet is Julie. Oh, I'm going to kill her name. Forgive me, Juliet. Juliet is, 2 miles, 2.5 miles northeast. Let's just make it easy here for the example. Okay. So the northeast might indicate that she's at a 45-degree angle here. Okay. So that might be another way you could indicate her direction. But the point is that displacement itself carries with it both a magnitude, all right, the 2.5, and the direction, 45 degrees or northeast. Okay. So that's the idea of vectors. All right. Well, we can't really make a living here mathematically by constantly having to depend on drawing these guys. Okay. So we need to come up with a better shorthand for vector quantities. So let's talk a little mathy here. All right. Let's say we've got a vector in a plane. These are planar vectors, by the way. They're not spatial vectors. We're not talking about a vector in space. We could talk about that, but we're only talking about vectors in the plane here. So, we've got an x-axis, right, and y-axis. And so here's some vector out here. Okay. Well, whenever we're working in an xy frame of reference, we always have the nice the convenience of being able to label points. Okay, so what we can do here is we can call this point, we're going to call this the initial point, and we'll give it the coordinates. We'll give the point the letter P, capital P, and we'll give it the coordinates x1, y1. Okay, this is the initial point. Initial. Okay. This point here at the end of the arrow, the tip of the arrow there, the tip of the directed line segment, is called often the terminal point. We'll label it Q, and we'll give it coordinates x2, y2. And this is called the terminal point. Well, again, we could carry around x1, y1, and x2, y2. We could do that. However, excuse me while I get a drink of lemonade here. However, that also is a little bit awkward. And so what we could do is we could move this vector to a position that would not disturb either its direction or its magnitude. Okay. Now the only way to change a vector's magnitude or size would be to shrink it. I mean, we could do that or stretch it, right? And that would create a whole different vector. The other way to change a vector is to change its direction. And the only way to do that is to rotate it somehow in the plane, all right? But to preserve both of those things, what I could do is I could grab it here, and I could move it like that, okay? See what happened there? I moved the initial position. Yeah, I didn't mean to move the y. I moved the initial position to the origin. All right. When a vector's initial position is at the origin, we call that position standard position. All right. So when the initial point is at the origin, all right, we say the vector is in standard position. Well, okay. I mean, that's nice and all, I suppose. And we can do that. Let's go ahead and put our guy back up here, though. Oop, let's see. Let me go ahead and grab these guys again. That's probably not going to work. All right, let's do this. Let me just grab him, and we'll move him up. Okay, like this. Okay. And how about if I grab this stuff here? I'll move that guy back up there. Oop. Okay, well, there's Q, right? Here's that original P. Okay. There we go. So there's Q, right? I'm not sure if I can grab P. Let me see if I can grab it. Okay, not bad. All right, so we put it back into this original position. So how would we though find length and direction, or magnitude and direction? How would we do that? How would I find the magnitude of the vector? Well, magnitude is the length of this vector, and if you think about it, this would just be the distance formula, right? Remember the distance formula from, I don't know, from Algebra 2 or Algebra 1 or geometry or something. So the magnitude of a vector is equal to, it would be equal to what? The square root of x2 minus x1 squared plus y2 minus y1 squared.
Hey, Mr. Boach,
Hey.
is there another Ray that can just sit in here and
Absolutely.
take? Because I'm doing the same thing on the board.
Ray, come on in, come on in.
Thanks, Ray.
Hey, I'm recording.
Yeah, okay,
Close
all
it,
right.
yeah. I like your haircut.
Well, thank you.
I'm recording video, so it's going to be weird here. I'm talking.
Okay,
while,
yeah,
all right.
that's cool.
All right, so yeah, no, the kids are going to laugh hearing this, but
Hey, guys.
yeah, yeah. Reagan Robichaux's in here taking a quiz. So all right, or test. All right, so the magnitude of the vector would be determined that way, right? Well, that's kind of a pain. You know, how would we find out this direction? Let's talk about this direction here. I'll call it theta. Well, to find out theta, what we could do is we could take recognize that the tan of theta is equal to y2 minus y1 divided by x2 minus x1. And we probably shouldn't solve for theta, and the reason for that is, if you guys remember, arctan is not an exact, it's not a natural inverse function. So to make sure that we get the right direction, we have to really look and understand what quadrant the ray is pointing in. So we'll come back and talk more about that, but that would be the relationship between the direction of the vector and the coordinates there. Okay, so the point I was making earlier is that it's a pain in the rear. Is this going to be bugging you, me talking like this?
Oh, no.
All right. I really do have a haircut.
Thank you.
The point of us putting this thing into standard form was really so that we only had to deal with one set of coordinates. Okay, so imagine if you will, a vector in standard form. So let's change slides here. We'll look at standard form. Standard form or standard position. Okay. So again, I just want to remind you that the way, let me see. I guess I didn't mention it before, so let's talk about this again. So if I've got a vector, P, Q, and I wanted to move this vector into standard position, all I would need to do is to undo the initial point position. Okay? And when I undo it, it would naturally take me and go like that with the vector. Okay? So, the question is, how do I undo it? Well, the way to undo it is by subtracting the x1, y1 coordinates from essentially, in reality, all the points of the vector, but all you really need to do is subtract it from the terminal point. Okay? So, to undo the initial point, we can do the following. X2 minus x1, comma, y2 minus y1. Now, when I do this, it results in the following vector. Right, so I'm going to, I guess I'm going to draw this again. Right, now I want you to notice here that it does not affect the direction or the length of this vector at all. Okay? All it does is it puts the vector in a really nice, convenient position for us. The initial ray, the initial point is the origin, 0, 0. And the terminal point is, the coordinates are these coordinates here, x2 minus x1, y2 minus y1. To communicate to a reader that the terminal point is, or that the vector is in standard position, we change slightly the parentheses of the ordered pair, and we write them this way. All right, it look like less than, greater than signs. So x2 minus x1, comma, y2 minus y1. whenever you see this notation, this greater than x, this greater than less than notation, this notation means that the coordinates are the coordinates of the terminal point of a vector in standard position. We call this form component form. Okay. All right. Now, one more thing before we leave this slide. How would I find the magnitude and the direction of a vector in this form? Well, it's the same thing, right? If you look at this, the magnitude would be the same. Which, again, suggests that we haven't changed the vector at all, which we haven't. Right? And also, the direction is still the same, right? If you think about it, this is, if we call that theta, and this is y2 minus y1, from the original, y2 minus y1, this is x2 minus x1. You might be thinking too, what happens if these are negative, you know, if these differences are negative? Well, the tan relationship would still be the same. In terms of the direction though, you'd have to know which quadrant you're pointing in, because arctan, if you think about it, arctan is only going to give you directions in the first and fourth quadrants, right? Something positive and something negative. So we'll talk about that, but you'd have to, if your vector was pointing in the first or third quadrants, you would need to be aware of that. But in terms of this relationship would still hold. Tan theta is this ratio, y2 minus y1 over x2 minus x1. Okay. Before I leave this slide, let me introduce you to some notation as well. Okay. So, if you read in a textbook and you see, and they want you to think of a vector, we'll call it v, as being in fact a vector quantity, the textbooks will usually make the v or whatever letter they're using really bold face. Well, you really can't do that in a when you're writing on a board. And so what we'll usually do is we'll go like this. We'll put a little half arrow above it. All right. So this is a vector v. Okay, v indicates vector. Indicates a vector quantity. Okay, so you got to put a little arrow. You need some kind of conventional shorthand to indicate to the reader that you're talking about a vector quantity. So usually it's this little arrowhead over the top. At least that's the way the University of Michigan professors always did. All right, so there's v vector quantity v. The magnitude, we use what looks like absolute value bars. So when I write vector like that, and a lot of times they'll do double bars, just to emphasize the fact that you're finding not technically absolute value, but a length of a vector. All right. So this is the common way to symbolize or denote the magnitude of v. And one more thing I'll mention, theta here is the direction, in this case it's called the direction angle. Direction angle. Okay, all right, I think that's all the notes you need to do some of these problems. All right, so I'm going to be working problems off page 454. And I'll give you some to do for homework as well. I know you're not excited about that. That's fine. Reagan always loved to do homework. So she's laughing back here. All right. Let us begin with number 11. What Dr. Larson wants you to do here is he simply wants you to show that two vectors are equivalent. Okay? Well, how would you do that? How would you show that they're the same vector? Well, two vectors are equivalent if they have the same magnitude and they have the same direction. So let's demonstrate that here. Okay? All right, so I'll write that. That's worth writing. Vectors are equivalent if they have the same magnitude and direction. Okay, so he labels one vector u and the other vector v. These are very common letters denoting vectors. All right, so let's find the magnitude of u. Well, that would be what? Square root, just the distance formula, right, of 6 minus 2 squared plus 5 minus 4 squared. And that is equal to radical 4 squared of 16, 1 squared is 1, so radical 17. V's magnitude is square root of 4 minus 0 squared plus 1 minus 0 squared. And that's equal to also radical 17. So their magnitudes are the same. What about their directions? Well, they're both pointing in quadrant 1, but that alone, you know, they're both sort of pointing in the northeast direction, but that alone isn't good enough. You have to really establish that the tan of both direction angles are the same. So, if you go back to earlier things that we wrote, let's check the tan ratio of the theta, the direction angle of u. All right, how about that? So that would be what? That would be y2 minus y1 over x2 minus x1. So 1/4, right? And then the tan of the direction angle for v would be, again, y2 minus y1 over x2 minus x1. Notice here too, v is in standard position, isn't it? So all I really needed were the component coordinates, the 4 and the 1 there. But anyway, so 1/4. All right, so the ratios are the same. Now, to be fair, it should be noted that if these guys were pointing in the exact opposite directions, you would still get the same tan ratios. So you're going to have to establish the fact that they're not pointing in opposite directions, but in fact they're pointing in the same exact direction. Okay. Anyway, okay. So these guys are clearly equivalent. All right. That's all. That's what he wanted to do with 11. All right. Look at 15 and 17. You're not getting as good a drawing as what Dr. Larson has, but I think it'll be instructive. All right, 3, 5. -1, -1. Hey, were you the one that invented calling Josh Larson? One of you guys.
It was Bella and I. I think it was a collective.
These guys, this trig class, or pre-calc class.
Trig, excuse me?
No, I'm sorry. Yes, I know. They don't understand the whole Larson thing. It's carried over into calculus. It's carried over to calculus, but they don't. These guys don't do the whole Larson thing.
That's sad.
So. Okay, so how do I put this as vector v? How do I put this guy in component form? Well, remember, component form looks like this. We use this notation here. Sometimes, just notationally, we might write this, v1, v2. We'll use the letter they use for the vector here instead of x's and y's. Sometimes they'll do this. Actually, not v1, sorry, vx. Vx and Vy. All right, this is component form. Well, to get this form, we simply have to subtract the initial points, initial coordinates from the terminal. So 3 minus -1, comma 5 minus -1. And this makes sense if you think about it. We're trying to undo the -1, -1. All right. Remember, we want to undo this. Well, undoing without twisting or lengthening just means it's a rigid transformation, right? It's a slide to the right 1 and up 1. Okay, so you're subtracting or you're undoing these coordinates. So we get here 4, 6. All right, this would be the component form. Component form of V. Right? It's V. These coordinates. These terminal coordinates. Let me try to write that here for you guys. Terminal coordinates in standard position. Okay. You leaving?
Yeah.
All right.
Have fun.
Thank you. I'm glad you could stop by.
Me too.
All right, look at 17. Yeah, in about 5 minutes here, guys, the third period class is going to come in, and so it might be a tad bit noisy, but I'll make sure they're quiet. But you might hear me saying something to them. All right, number 17. And at this point here, the terminal point is 3, 3. initial point here is 3, -2. So again, you're undoing this, right? So you're moving this vector left 3 and up 2 to undo the positive 3 and the negative 2 in the coordinates. Right? So to do that, again, he calls this V. So V in component form would be 3 minus 3, comma, 3 minus -2. Right? So V in component form would be 0, would be in the position 0, 5. Okay. All right, and let's do one below there. How about 23? So 23. They don't draw a picture of this for you. They just tell you what the coordinates are. So the initial point. Let's just call it initial for heaven's sake. The initial point coordinates are -1, 5. And the terminal point coordinates are 15, 12. So this vector, they don't even name it, this vector in component form would simply be 15 minus -1. Again, you're undoing the -1 along the horizontal position of -1, which means you have to subtract that coordinate. In other words, you're going to end up adding 1 to the 15. And then you're undoing 5, so you got to bring the terminal point down 5, right? So 12 minus 5. So your component form here would be 16, that's the x position, right? And 7. Okay. All right, let's talk a little bit now about adding and subtracting vectors. Okay, so let's talk here adding and subtracting vectors. Well, right now, let's just do it graphically. We'll talk about how to do it analytically in just a minute, but let's just focus on graphically. Okay, so again, if you're looking at your book here, this is 25 through 30 here. It gives you these vectors here, U and V. Okay, like so. And he wants you to do some vector operations with these guys. Graphically, he wants you to do some things. And so let's do the ones that he has here. So 25. He wants you to do -V. I'm going to use color here. I hope you don't mind. -V. Well, this is the first time we've seen something like this, where you have a. Okay, guys, there's the bell. I'm going to keep working here, but the third period kids are going to come in. All right, so just be prepared for me talking to them a little bit here. All right. Hey, I'm recording the lesson, guys. So, anyway, I need you guys to be quiet when I'm coming in. This is all going to be. Yeah, thanks.
I'm just gonna get a snack.
Yeah, that's fine, bro. That's fine. Okay. So let's talk about what this means, negative V. Well, if you think of V as having components, or having a component form, right? Vx, Vy. This negative we call this a scalar, right, or a scalar multiplier. And when you multiply a scalar to a vector, that multiplier just goes inside the component notation, and it, in a sense, it distributes. That negative is going to end up going on both the Vx and the Vy. So this would produce negative, let me stay negative Vx and negative Vy. Well, what does that do to the vector in the picture? Well, when you gate the components, it literally just turns it around. Hey, buddy. Hey, I'm recording something, so I don't want you to think it's weird. Like I'm talking into a recording. So.
Oh, sorry.
Yeah. No, you're cool. You're cool. I just want you guys to know what I'm doing. So, negative V would end up then looking like the following.
Mr. Roach, have you been drinking an entire gallon of lemonade?
Pardon?
Have you been drinking an entire gallon of lemonade?
No. I found that in the fridge downstairs, and I forgot my tea today. So. Hey, I don't want you to think I'm weird, but I'm recording something. So I'm talking like it's going to be looking like I'm talking to myself, but I'm actually recording it. Okay. Yeah, that's fine. That's totally fine. Yeah. So, all right. So that would be how we would draw a negative V. If the coordinates of the original V have just been made opposite, then that's what you get. All right. You can see that if you think about it. This would be V. Whoa. This would be V1, right? V2, and so this would be negative V1, negative V2. Oh, actually, sorry. Sometimes I forget. We use X's and Y's here. That's my bad. So Vx, Vy, negative Vx, negative Vy. Okay. You don't have to do all that work. I just wanted you to explain how we get the picture for negative V. All right. How about, let's do 27. 27 is U plus V. Well, to do U plus V, let's think about what it means in terms of components for just a minute. So let's consider what this means if we had these vectors in component form. Well, it would look like this. It would be, okay, hey guys, listen, hey, if you want to work outside that, you can. I just need to be quiet so that you don't show up on the recording.
May I go study in the morning?
Yes, go. Yes. Yes, you're very welcome.
Also, thank you for telling us to get.
Yeah,
I was like sending her email.
I know. She called me, so it's my fault. I just, yeah. So U plus V would mean, literally, Ux and Uy plus Vx Vy. Yeah, that's fine. That's fine. Thanks, guys. Thank you. Well, to add this, just think about what it would mean to have, let's say Juliet. Let's pick on Juliet again, and we'll say that she's on the Girl Scout trip, and let's say that Juliet goes. She's on this hike and she goes 5 miles east and then 2 miles north And so she ends up right here. Okay, so that's her first displacement, right? 5, 2. Now let's say from there she goes back west, but she still heads north. Okay, so if she were to go back, let's say west 2 miles, and then north, let's say 4 miles. All right. So she's going back this way and then this way. And so her displacement from this original position, or not the original, from this first position would be there, right? Okay. So we could write this displacement in component form this way, right? -2. We have to use a negative sign there to indicate that Juliet's gone left or gone west, okay? And then +4. Well, so where is Juliet now? Okay, help Juliet. Where is she? Well, she is here, right? But where is here? Well, that would be 5 minus 2, right? Okay, so she's 3 miles, or she's 3 units to the east. Yeah, guys, I know it looks weird, but I'm recording something here, so if you want to study out there, you can. It's totally fine with me, okay? She's 3 miles now east, where she was 5, but she came back 2, right? Okay, -2 there. And then she's now 6 miles north. Okay, so this really shows you how to add vectors graphically. All right, we call this the head-to-tail method. It's one way to call it. The other way to call this, or the other way we say this, is we refer to it as the parallelogram method. So you can imagine here, if you think about the 2 vectors that were added here in this illustration, think about them as being 2 consecutive sides of a parallelogram. So if you kind of filled out the parallelogram, okay, and maybe not the best, but I think you get the idea. Then the sum of the vectors is from the beginning of that first vector, right, across to the tip of the last vector when they're added head to tail. So it's this diagonal, right? It's this particular diagonal that you get when you add. All right, so that's one way to add vectors. So if you come back here, let me just finish this little line here. So if we're adding these vectors here, all we do is we just add the components. So this would just be ux plus vx, comma, uy plus vy. Okay, like so. Well, in our picture, the way that we would do that is we would slide. We could slide this vector. I'm not sure if it'll let me grab it. Let me see. Oh yeah, we can. So we could slide that vector like that, right? We preserve its length and we preserve its direction. We can't twist it or stretch it or shrink it. Rotate it or stretch it or shrink it. So the sum, the answer to 27, would be this vector here. Let me use blue. Okay, that would be u plus v. All right. Well, let's look at a couple more here. Look at 29. I'm going to go ahead and copy those vectors back down again. So here's u. So this is v. Let's do a couple more of these. I think they're important to do a couple more examples. In particular, what about subtracting? Right? What about subtracting u minus v? Well, there's a couple ways to think about u minus v. One of the ways is to consider this as being equal to, and it is, equal to u plus negative v, right? And that's really consistent, very consistent with how you learned when you first, you probably don't even remember this, but when you first were learning about subtraction, you would change the sign of the minus sign to plus and then add the negative sign to the next term. I'm not sure exactly how the teacher says it, but that's how you learn subtraction, right? Plus negative. And so that makes sense. We could do it that way, all right? Or my favorite way, though, actually to do it is a little shorter, and it's let me explain my way, and you may hate it, I don't know, but when you're looking for when you're trying to combine two vectors, a lot of times we'll call the combination a resultant. So I'm going to just for the sake of the example right now, I'm going to call this R like that. All right. So what is R? Well, R would be the vector, okay, that you would add to V to get U. Now, addition of vectors, I think, is much more intuitive, okay? So if we look at our picture and we say, well, what would I have to add to V to get U, all right? Well, remember, we add head to tails, and so what I would add to V to get U would simply be this guy. All right, so that's just consistent with how we understood addition of vectors in the last slide. Okay, so there's the difference. This is R is equal to here u minus v. Well, you might think, well, I'm not going to ever remember that. Well, here's what you can remember. This is extremely helpful. Okay. If you're ever wanting to add or subtract two vectors, the easiest thing to do with those vectors is to first put them in a position where they have the same initial point. They don't both have to be in standard position. If you're just drawing a picture, then here, let me give you an illustration here. So let's let this guy be. We'll call this guy X, and I'll call this guy Y. Okay. Now, if you want to add or subtract them, then the first thing you would want to do is to move them into a position where they have they share a common initial point. Okay. I'm going to go like this. The next thing to do is to fill out to finish the parallelogram, right? Okay, so parallelogram. So this is called the parallelogram method, but it works for both addition and subtraction. This is kind of cool. So if you wanted to add x to y, by the way, vector addition is commutative, just like scalar or number addition is. You can add in any order. So you can think of that as the x vector. You can think of this as the y vector if you want. All right. But x plus y then would be this resultant here. Right? Remember, we talked about this earlier. It's from the initial point, this shared initial point, to the other diagonal, the opposite diagonal in the parallelogram. All right, so there's x plus y. X plus y. Well, what would x minus y be? What would x minus y be? Well, x minus y, go back and look here, okay, to help you understand this. X minus y would be the vector that you would add y to get x, all right? Well, here, you come back here and look at the parallelogram. We have y. The vector that I would add y to get x is this guy, right? This would be x minus y. Okay, see, notice how, this is what makes the parallelogram method so cool, okay, is that along this diagonal, the diagonal, I don't know if you want to call it the main diagonal, but it's the diagonal from the common initial point, to the opposite vertex, or vertice or corner, whatever you call that. And it's the other diagonal. It's the other diagonal that forms the difference of the two vectors. Okay. Now the only thing I might add to this is that there is a difference between x minus y and y minus x. Okay. Now it's not magnitude, but it's just direction. And so if you were doing y minus x, you'd be looking for the vector that you would add x to get y, and that would just be this guy. Okay. Let me use purple. Okay, so we'll use purple. This guy here, right, coming in this direction would be x minus y. Totally cool. This is what makes the parallelogram method so nice. All right, if you go back to our picture here, you can see it again, parallelogram. Right. Notice again, u minus v starts from the head of v, okay, the guy you're subtracting, and coming back to the guy you're subtracting from. This is the r here in the picture is the vector you would add to v to get u. Okay, so a little lesson there on adding and subtracting vectors. I hope that made some sense. I'm going to give you probably, let me see here. How about if I do number 30? Let's do number 30 here, okay? Try to stay away from these because I usually give you these evens, but they don't have any more good odd ones. All right, so how would I do v minus half u? Well, again, you're going to start at the end of half u and come back to v. All right, if you again just review how we did u minus v in number 29. So, but I have to do half u. Okay, so in my picture, and maybe this will help. Maybe this will help again. Let me do purple here. So you're looking for this vector r, and this vector r is the vector you're adding to half u to get v. Right? So come back, I guess, to the picture I've drawn here in number I've already drawn. So let's go. I'm going to work in purple here. So let's first go ahead and find half u. Right? We're going to start with half u, and we're going to add a vector then and get out to v. So here's half u. Right? Half of u is just literally we're shrinking u in half. Okay. By the way, the half does the same thing that the negative sign did back in number 28. So half, if I think of u in component form again, ux, comma uy, this just equals half ux, comma half So what that gives me is just a vector pointing in the same direction. It's exactly like taking a triangle and reducing the size of the triangle. You're really not changing the direction of the sides, you're just making it smaller. So in the picture here, there's half u, this is the vector half u, okay? Well, what would I add to that? That's the r, all right? What would I add to that to get v? Well, if v is my final vector, what I'm going to do is I'm going to go from u out to, half u that is, out to the head of v. All right, so there it is. That, the purple vector there is v minus half u. Purple vector. So just try to remember, you're going from the vector, the vector or the scalar multiple of the vector that you're subtracting to the head of the vector you're subtracting from. Again, it's a nice little method, and if you just remember the parallelogram method we talked about, it should be okay on those. Okay. All right, well that's adding and subtracting vectors. Oh, one other thing I should mention here before I leave this slide is the zero vector. We do have a thing in mathematics called the zero vector. And the zero vector is simply the vector that has no direction or magnitude. I mean, it's just kind of like the zero, in math. You can add it to anything, it doesn't change anything. So this is the zero vector. You might sometimes see it like this, denoted like a big zero, but because you want to communicate that it's a vector, you put a little vector bar above it like that. Make the zero vector. We'll make them happy. Okay. All right, let me go to the next page. I'll probably just end up doing one. Well, no, I'll do a couple of these. Again, I know you don't have a book. If you're doing this with a book, I'm on page 455 now. And let's do, he wants you to do three things here. He wants you to find A, U plus B, and B, U minus B, and C, I want you to do 2U minus 3B. Again, I want to say that these are called scalar multiples, scalar multipliers. Right? The two here is called a scalar, right, or a scalar multiplier. I think I mentioned it before, but just in the context of a negative sign. But I'll say it again. All right, so number. Let's see. Let's do number. How about 30 through 31? We'll do 31. All right, so let me write 31 here. 31. And 31. U is 2, 1. These are component forms. Again, you don't need. If you have these vectors in component form, then it's simply easiest to use the components. You're just using these components to do the addition, subtraction stuff. So 2, 1, and then V is equal to 1, 3. Remember, the initial. This is like these are the terminal points. The initial points are 0, 0. And all you need, though, when you have component form, are the components. Okay, when you're doing addition, subtraction, if you're finding magnitude or direction, you just need the components again. All right. So, and I'll say another word about that some more exercises. So u plus v, okay, this would just be what? 2, 1 plus 1, 3. Again, it's like, you know, going 2 miles east and then 1 mile north, and then going 1 more mile east and then 3 miles north, right? So the final position, if you will, if you're thinking about it as a displacement or position vector, would be 3 miles east and 4 miles north. Okay, u minus v, let's do that in blue. So 2, 1 minus 1, 3. Well, remember that this acts just like a scalar as well. So it affects both the coordinates inside here, all right? So to subtract this vector, you literally are subtracting each of these components. So, again, using position, it's like going 2 miles east, but then coming back a mile, or going a mile west. So where are you? Well, you're still a mile east. You went a mile north, but now you're going down 3 miles, or you're going 3 miles south. Okay, so you're 2 miles. Well, you're 2 miles south from that original position, right? You were 1 mile north of the original position. You've gone 3 miles south, which means you're 2 miles south of the original position, so -2. Okay, so in the final case here, all right, 2u minus 3v. I think you probably can see what's going to happen here. Again, the 2 and the 3, all they do is just lengthen both components. It's very similar to you know, that notion in geometry, that's similarity notion in geometry. If you were to preserve the shape of something but just change its size, all the components for all the points would have to change proportionally. So that's really what's going on here. If you're doubling a vector, notice you're not changing the direction. You're basically just changing the magnitude. You're literally doubling the magnitude, which means you're doubling. If we're multiplying this first vector by 2, if you think of it as going 2 miles east, 1 mile north, now that we're going 4 miles east and 2 miles north, right? And the 3 does the same thing here with the v vector. Now we're subtracting them. So what do we get here? In the end, we're going to get 4 minus 3, so 1, and 2 minus 9, -7. Okay. All right, let's talk now about 2 additional ways to write vectors. 2 additional ways to denote vectors. So the first way I need to do for you or show you is I want to introduce this idea of a standard unit vector. Standard unit vector. Standard unit vectors. Okay. Well, you know what a vector is now. What does unit mean? Unit essentially means 1. Okay. And so a unit vector is a vector of length 1. Now, remember that a vector can point in any direction, or it has a direction as well. So just by saying a unit vector, that doesn't tell you there's an infinite number of unit vectors. They could, you know, a vector of length 1 pointing in any direction. There's an uncountably infinite number of those. Standard all right, refers to two particular positions, all right? So the first one is the vector that points directly east or along the positive x-axis. This vector is denoted by an I, okay, like that. Now, you could put a vector bar above it, but because it's a special vector, we put, usually when people are writing, they put a little cap like that above it, all right? So that guy represents the standard unit vector, the vector of length 1 that points in the positive x direction, okay? So just again, to make sure you're cool with this, it has length 1, unit vectors, all right, their magnitude's 1. This particular vector points in the positive x direction, positive x. All right, you can think of it as east. All right, the other standard unit vector that we'll be working with is the one that points, it's one long, but it points in the north direction, all right? Okay, and he's denoted by the letter J, and again, we put a little cap over him, all right? So I and J. Now, if we were working with vectors in space and we needed the standard unit vector in and out of the board, then that guy is denoted by a K, all right, IJK. Anyway, we're just working with I's and J's. So J is one long, same thing, J is one long, and he points in the positive Y direction. Or north. Okay. All right, so let's look at, and I know I said there are two ways. We'll come back just in a minute and talk about the second way. All right, let me do number, if you don't mind, let me do number 35 and 37 here. So 35, I'm given u, some vector u is equal to 2i, and v is equal to just j. Now, what's important, if we're going to add, subtract, and do a scalar, another scalar operation on these guys here, what's important is to understand that this is just a way, the standard unit vector notation is just a way to distinguish between up-down direction and left-right direction. So you can think of these coefficients in front of the i's and j's as just being the values of x and y. So if you wanted to, you could take u and you could write it in component form this way, all right? 2i would mean 2 along the positive, 2 as a position along the x-axis, and then nothing on the y-axis. So that's what that vector would look like in standard, in component form. Likewise, the vector j in component form would just look like this, 0, 1. Okay? So, A, u plus v, well, what would that be? That would just be equal to, let me do this in green, 2, 1, or 2i plus j, right? And since the original vectors were given in the standard unit vector form, you really should do your answer in the standard unit vector form. Let's see, bu minus v, bu minus v would be equal to what? 2 minus 0, 0 minus 1. So that would be equal to 2i minus j. And then finally, c 2u minus 3v, 2u minus 3v would be equal to 2 times 2, 0 minus 3 times 0, 1. And that would give you, what would that give you, class? That would give you 4 minus 0, so you'd have 4. And then 0 minus 3 would be negative 3. Okay, so that's using, so that would be what, 4i minus 3j. Okay, that's the way you really would want to write it. So let's smile. Let's put our smiley face on this guy. Okay. All right. All right, let's talk about the other way. I'm kind of inserting this in a weird place. But he doesn't really ask you about this directly yet. But the other way to write a vector. Okay, so let's go back and let's think about a vector in component form in standard position. So here's V, and we'll call this Vx, Vy. Well, again, let's recognize that the magnitude of V, we can write this way, magnitude of Vx, Vy. That would be equal to, again, the square root of Vx squared, right? Vx minus 0. Since the initial point is at 0, there's nothing to subtract from, so you can just use the components as the values, or not lengths really, but the positions, if you will, of the x, the horizontal position of the vector, and then the vertical position of the vector. So those, once you square them, the negatives would go away if they were negative at all. But so Vx squared, right, plus Vy squared. And that would be the magnitude, right? The direction, what would the direction of the angle be? Well, the direction of the angle would simply be given like that, theta, okay? And the relationship that you'd be interested in there would be tan of theta. You're looking for it. And you would recognize that, that the Vx vector, okay? Right, this would just be Vx, or you could think of this as you could think of this as a vector, right? And call it Vx. This Vx without a bar would be like a scalar. That would just be the number. So to make it a vector, you'd have to call like that Vxi, and this would be Vy, the component, the scalar value, the component j, like that. Vxi is Vyj. Right, so you could write that. You could say V is equal to Vxi plus Vyj, which is the same thing as, in component form, Vx, comma Vy. Okay, like that. Well, again, so the tan would just be, the tan ratio of the direction angle would be equivalent to Vy over Vx. Right? We kind of established that. Well, let's think about another way to write the Vx and the Vy. Well, how about going all the way back to SOHCAHTOA? All right? SOHCAHTOA would let us think of the Vx component as r cosine theta. Well, r here is just the magnitude of v. So I could write Vx, the component, as the magnitude of v cosine theta, right? It's a legit way to do it. And likewise, I could write Vy as the magnitude of v, what? Yeah, that's right, sine theta, right? Okay, so this gives me a third way to write a vector. So I could write the vector this way. I could write v as being magnitude of v cosine theta, comma, magnitude of v sine theta. Yeah. And then I could notice, because the magnitude is just a number, right? The magnitude of v is just a number, so it's just acting like a scalar here. I could just pull it out and write it this way. Magnitude of v cosine theta, comma, sine theta. Totally sweet. All right, so this is the final way. I don't know if Dr. Larson gives this a name. You can think, I don't know. I've always looked for it in the book. I don't see a name in the book, but you can call this the trig form if you want. Trig form of the vector. Okay, trig form of v. Trig form of the vector v. How about that? Okay. It's so when we say trig form, that's what we're talking about. All right. So come back up here. Come back up here. This was the. I'll stay in green. This is the component form, right, of the vector. And this is the standard unit vector form. Standard unit vector. Okay. So there are three forms, all right? Standard unit vector form, pink, component form, and trig form, all right? Okay, hey, you get used to those and review these pictures as you need to as we're working through problems here. All right, let me do just a few more here. I want to talk about finding. This is an important thing. Maybe we'll end. I'll do a few extra problems, but we'll end in terms of the notes. We'll end with this. Okay. Finding a unit vector in the direction of a given vector. Okay, this is a very important skill, if you will, all right, to be able to do. So let's talk about this. This is gonna bring us to problems 39 through 48, and I'm gonna try to work through. Maybe down to the 60s, but if you're looking at a book, it's not that far if you're looking at the problem. But this is probably the last thing I need to do in terms of notes, okay? All right, so find a unit vector in the direction of a given vector. All right, let's talk about how you would do that, all right? So here, look, here's a vector. We'll call it V, okay? Well, the easiest way to find, remember what unit means, okay? Unit means that it has length 1. Okay, so this vector here, unit vector, has a length of 1. Unit length, we would say, all right? Length equal 1. Or magnitude equal 1. All right, so the easiest way to find a unit vector would simply be to shrink in the direction of the given vector, okay? Would simply be to shrink the given vector v down to unit size. All right, well, how would I do that? How would I shrink v down to unit size? Okay, well, it's actually very straightforward. The way to shrink v down to unit size is to take v and divide by its magnitude. All right? In other words, if v was 10 long, all I would have to do is divide it by 10. And I would get a vector in this same direction, okay? But with unit length. So this is equal to a unit vector in the direction of v, in the direction of v. Okay. So like again, like I said, if v was 10, you divide it by 10, you'd end up with a unit vector down here, right? So this would be of length 1. That's the guy. That's what this guy would be. This guy would be v, the original vector, just shrunk. All right. In other words, divided or multiplied by 1 over its original magnitude. Okay, that would be this guy. Okay, look at 41 and look at 47. Look at 41 and 47, all right? Okay, so what are they asking us to do here? They're asking us to find a unit vector in this guy's direction, okay, but of unit length. So again, you don't have to draw the stuff I'm drawing. I just want you to understand it. So we've got this vector here, right? -2, 2. And we're trying to reduce this guy down to unit length, right? Somewhere in here, kind of. Right? So we're trying to find that guy. Well, the way to find that guy, again, we talked about it above, is to just divide by the magnitude to divide v by its own magnitude. That would reduce it down to unit size. Well, we haven't been asked to find a ton here, unless I've just overlooked it, the magnitude of vectors. But here's a trick. I want to introduce this idea to you here. This is a very convenient problem to show you this with. When you're finding the magnitude of a vector, it's easy because you have to work with square roots, squaring and taking the square root of the sum of squares. It's easiest to factor out a positive constant factor from the components first before you actually do the square root work, okay? You don't have to. Some of you are not going to like this. But because I've got to find the magnitude of v here, I'm going to first rewrite v as 2, -1, 1. Okay, did you see how we did that? I just pulled a common 2 out. I don't like to pull a negative out because that changes the direction of the vector. It wouldn't actually change the final answer, but I still don't like to do it. Whenever you mess with the signs inside here, you would actually change the direction of the vector. So don't do that. Just pull out a common positive factor if it's there, if it exists. If it doesn't, then you don't have that luxury. Okay. But the reason why this is nice to do is that when you go to take the magnitude of this guy, okay, when you go to take the magnitude of this thing, this is the same thing as, and we didn't, by the way, we didn't really review, there's 8 properties that he lists in the book. To be real honest with you, they're not really worth the time to actually review all 8 of them. But one of them is kind of nice. If you think about the scalar 2 times the vector here, -1, 1, you can write this as 2 times the magnitude of negative 1, like that, right? Or technically, I should put this guy in absolute value bars. Once this scalar 2 comes out of these vector magnitude, double absolute value bars, you technically it comes out as its absolute value, all right? But remember, we're only going to pull a constant. If we do this trick, we're only pulling a constant out, a positive constant out, constant common factor out anyway, so you wouldn't have to worry about the sign on that guy. So this is equal to what? This is equal to 2 times the square root of negative 1 squared plus 1 squared. Now what's so nice about that is you don't have to deal with the 2 inside here. Okay, this is a lot easier to deal with. So this is equal to, if you did, it's fine. If you did, it'd still work out to be the same. But this is just a nice little trick for finding magnitudes of vectors that have a common factor in their components here, right? So 2 what? 1 plus 1 is 2, so 2 radical 2. Now for you guys that didn't do this, you would have gotten what here? You would have gotten, come over here, you would have gotten, this. Negative 2 squared plus 2 squared. And you would have gotten this 4 plus 4. And you would have gotten 8. And 8 is equal to 2 radical 2. So anyway, it makes it a little bit easier, okay? All right, so to find my unit vector then, I'm going to take, let's go over here. So V over the magnitude of V is negative 2. That's V. Or you could, I mean, if you wanted to use this, the other form of it, you can. In fact, here, let me do that. I think it is helpful to use the form where you've factored out the constant, the common constant, positive constant. So if you wrote a 2, negative 1, 1, because usually you have to simplify a little bit. Divided by what? Divided by 2 radical 2. Okay, like that. So the way that Dr. Larson would expect this, notice here, this part's nice. You can cross those 2's out. So you'd be left with here negative 1 over radical 2, comma, 1 over radical 2. All right, and that's equal to negative radical 2 over 2, comma, radical 2 over 2. Now, I won't take the time to do it, but you could check to see that this was actually pointing in the same direction as the original. All right. Notice that the tan ratio is negative 1. The tan ratio of our guy here is negative 1. The magnitude, you could check to see that it's actually 1. You can do that. I'm not going to do it. Oh, heck, I'll do it. All right. So if you did, here, come over here. I just want you to make sure you're cool. Notice the tan ratio here. The tan of the direction angle, 2 over negative 2 is negative 1. And it's pointing, again, it's pointing, the first coordinate's negative, the second positive, so you're pointing in the second quadrant. So is our blue guy, right? First coordinate negative, second coordinate positive, pointing in the second quadrant. And notice the tan of theta here for this guy, same direction, right? Radical 2 over 2 divided by negative radical 2 over 2, that's equal to negative 1. Same ratio, right? And the coordinates have the same sign. So we're pointing in the same direction. The other thing was, what about the magnitude? What about the magnitude of this guy? Well, the magnitude of this guy would be the square root of this guy squared, right, plus radical 2 over 2 squared. And what happens there? Well, here, I know that you're trying to watch this and listen. This is the magnitude of V divided by the unit vector. Okay, like that. So, what is this guy? This guy would be square root of 2 over 4, right, plus 2 over 4, and that's what? That's 4 over 4, which is radical 1, which is 1. And that's what it should come out to, right? Unit vectors have unit length, okay? All right, anyway, the blue guy, that is our final answer up here. That's what they wanted. I was just showing you some other stuff. All right, that's 41. What did I say, 47? All right, how about 47? W is I minus 2J. Yeah, he does. Actually, Dr. Larson asks you to verify that the magnitude is 1. So, yeah, we'll do it. All right, find a unit vector in W's direction. Well, again, unit vector in W's direction, unit vector in W's direction would be, again, the magnitude of W, or W, sorry, divided by its magnitude. Okay, and that is I. Now notice this time, the reason I'm doing this one is because it's in standard unit vector form. So I minus 2J divided by, can you see how to find the magnitude of this guy? It'd be what? The square root of 1 squared, that's the coefficient on the x or the I part, right, plus negative 2 squared. Okay, so this would be what? This would be I minus 2J divided by 1 radical 5. So initially you'd write this in sort of that intermediate form of 1 over radical 5I minus 2 over radical 5J. Okay? And to be more formal, of course, you would write radical 5 over 5I. Now let me do that in red, kind of like how it looks in red. Radical 5 over 5I minus 2 radical 5 over 5J. Okay. Now, he did want you to confirm that the magnitude of this vector was, in fact, 1. So let's do that. So the magnitude of radical 5 over 5I minus 2 radical 5 over 5J. Okay, magnitude of this guy would be square root of radical 5 over 5 squared plus negative 2 radical 5 over 5 squared. What is that? That is 5 over 25, right, plus 4, right? Square of 2 is, negative 2 is 4. The square of the radical 5 is 5. 4 times 5 is 20, so that's 20 over 5. So this is equal to radical 25. Oops, sorry, that's a 20. That's 25 right there. Okay, 25 over 25, which is radical 1, which is 1. It's what all unit vectors, the length of all unit vectors is 1, okay? All right, let me just do 4 or 5 more here. I don't need to do any more lecture stuff. Find the vector v with the given magnitude in the same direction as u. Okay, so this is 49 through 52. So for 51, they want you to find v, right, where the magnitude of v, they give you that is 9, and the direction of v is in u's direction, is u equals 2, 5. Okay, so they want it in that direction. Well, again, the easiest thing to do here would be to start with vector u. Okay, 2, 5. You don't have to draw all this, but so here's u, right? This is vector u. So to find vector v, all I need to do is lengthen u so that it would have a length of 9. Okay, that would be a vector, certainly in the direction of u, right? We're not changing it u's direction. We're just trying to lengthen it out to make it 9 long. Well, the easiest thing to do that, the easiest way to do that would be to start with u, okay? Divide by its magnitude. What does this do? What does this do? This makes it 1 long, and then multiply that by 9, right? That would give me a vector of 9 long, of length 9 in u's direction, okay? So let's do that. So we'll start with u, 2, 5. We'll divide by its magnitude, square root of 2 squared plus 5 squared, and multiply that by 9. So what does that give me? Let's go to green here. Right? So that gives me 9 over 25 and 4, radical 29 times 2, 5. And that would give me what? 18 over radical 29, comma, 45 over radical 29, boom. And of course, that's not really conventional. That's not a conventional way to write radical expressions. So finally, 18 radical 29 over 29, comma, 45 radical 29 over 29. Right? Use the component notation, though. You know, make sure you don't forget that. Boom, done. All right, so again, what did I do? I found a vector that was in the direction of u that was 9 long, okay? And the way that I did that was I first found a vector in the direction of u that was 1 long, right? This guy here, right? Unit vector in u's direction. And then I just lengthened it by 9 by multiplying by the 9 there, okay? Okay. Look at 53, look at 61, and we'll call it a day. I know it's been a long lesson. Look at 53. Initial point, negative 2, 1, and terminal point, 3, negative 2. And Dr. Larson would like you to write a linear combination. He would like you to write the vector as a linear combination of standard unit vectors. So he wants you to write this in IJ form. Okay, the easiest thing to do would be to first write it in component form. Okay, let's do that. So the component form of this vector, we don't need to draw a picture here. So the component form would be what? It would be 3 minus negative 2, negative 2 minus 1. So the component form of this guy then would be what? 5, negative 3. All right, so then what he wants is he wants this vector in as a combination of standard unit vectors. So the answer he's looking for then, here I'll use the blue on this part. Okay, my color obsession here. 5I minus 3J. All right, that's what he's looking for there. Then finally, one more. Let's look at 61. It says define the component form of V and sketch the specified vector operations geometrically where U, okay, so he gives you this, U is equal to 2I minus J, and W is equal to I plus 2J, I plus 2J. 2J. I don't know if you guys ever had. Back in Florida, we had a place to eat, an eatery, like a mid-level restaurant called 2J's, Toojays, I believe is how you spell it. It was pretty good. Anyway, 2J's. It just reminded me of that. I've never seen one around here. Look at 61. Find V is equal to a half times 3U plus W. Let's see again. He wants you to find that. Then what's he say about sketch the specified vector operations geometrically where U okay, all right, I guess we can do it. All right. Anyway, let's find this part first. So this is equal to half 3 2I minus 2I minus J plus I plus 2J. Okay, so that's equal to half times, let me switch colors here, 6I, right, minus 3J plus I plus 2J, and that's equal to half times what? 7I minus J. Okay, and then send the half through. Is that right? 617, yeah, negative 3, yeah, negative 1J. All right, then send the half through, so you get what? 7 halves I minus 1 half J. Okay. Now, he wanted you to sketch the vector operations here. So I'm not sure exactly if he wants. Well, I don't know. I don't know if he wants just the final version of the V or not, but we can kind of do this. So 2I minus J so there's 2I, 2 to the east, right, minus J, minus 1. All right, so here's U. Okay, that's U. And then W is I plus 2J, 1I plus 2J. So there's W. I don't like that. Okay, so U and W, there they are. Well, let's see. If I go back to this original, 3 times U just literally link. Let me move this guy over a little bit. Whoa. I'll do this guy. Yeah. Okay, So, okay, so 3u. I'm working here right now. Okay, let me color this. 3, see that? 3u. Well, what 3u does, it just lengthens the vector 3 times, right? So here's another u, here's another u. There's 3u right there, right? This would be where? The coordinates would be what now? This would be, oh my, sorry. The coordinates would be what? This would be 6, right? And this would be -3. You know, if I drew this halfway decent. Okay. 3u plus w. All right, let's add w to that. Well, w. Let's do w in blue. So w is what? It's 1 to the east and then 2 north, right? So 1 to the east and then 2 north. So I'm going back to -1 here. All right, yeah, hang on. Let me put it at -2 just so you can see this a little better. So 1, and I got to go back here to, I got to go over to 7, right? Let me put these other guys in here too. This is really sloppy, but that would have to be 3, 4, 5, 6, halfway. Anyway, yeah, I know it's not that great of a picture, but all right. So come over 1 and then go up 2, so you're right here. So here's W. You're adding W, okay? Over 1, up 2. So that's okay. So this would be 3u plus 2w. Let me do that in black. It's an intermediate value. No, I'll do it in purple. So we'll do that in purple. So there's this guy, right? Okay, that's 3u plus that's 3u plus w, and that would be what? That would be 7, -1. So how about if I write it as 7i minus j. And then lastly, what? I have to do the half. And we'll do that in red, okay? So the half does what? Well, that just halves everything. It shrinks this vector back down to half size, you know, somewhere in here, right? Shrink this purple vector down to half size. Well, what would that do? That would mean, you know, this would be, the red vector would be my final vector. And that guy would be what? 7 halves. Let me write it like this. It's getting crowded here. 7 halves I. Okay. But you're also halving this this -1 distance too, right? You're coming up 2. You're halving this. You're halving the vertical distance as well. It was a -1 over here, the blue point. Now it's at -half. It's not pretty, but minus half j. And that's what the red vector, the final red vector, should represent. I know it's probably not drawn real well, but that it should probably be more right there. But, oh, anyway, okay. I hope you got something out of that. All right, guys. Hey, I'll see you on Friday, and I hope these notes help. Okay. All right. Bye.